So this is the very last video based off of continuing the discussion with diffraction patterns. And in particular, we're going to talk about what's called diffraction gratings. So this is actually kind of almost exactly what we talked about with the interference patterns. So here, the only main difference is that instead of having two slits or having one slit, we're going to end up having thousands and thousands of slits. Now, what this ends up doing, the main difference between a normal double slit interference pattern and a diffraction grating interference pattern is mainly the definition between each of the fringes. Um, so what we end up having is that these fringes will now end up becoming much sharper than they were originally. So this picture basically was supposed to would represent typically what you would normally see for an interference pattern of just two slits. You have the bright fringe in the middle. You have a later fringe on the side, but for the most part, it's a very wide fringe. If you were to see this as a physical example, you would kind of almost barely see the dark spots. It would be fairly hard to actually see the minimums. But when we have as we get more and more lines, more slits involved, we go to hundreds or thousands of slits, then the peaks become much sharper. Of course, we do still get a little bit of constructive interference occurring, mainly because while some of the waves may end up being constructively interfering with each other, or while some of the waves may be destructively interfering with each other and not producing much of a wave, there will be some that are constructively interfering. So you do get these smaller peaks, but the areas where pretty much all the waves end up constructively interfering will end up occurring, and it will become much sharper because of that, because they're all combined at one spot. And then once you deviate even a little bit, all of a sudden you get a majority of them no longer constructively interfering. So this in this diagram, this example A is representing two slits, while example B is actually representing six slits. All right. So this is just kind of something similar. We could take a diffraction grating and shine white light on it. So this is kind of what you would expect for that type of scenario. We have white light in the middle because all the colors are combining there. And just like with the interference pattern, where different wavelengths of light will end up diffracting differently, and their locations of each of their maximums will occur at different spots. The same thing is going to occur here, where we shine white light there. Blue light won't diffract as much, so it will be its first minimum and first maximum and second maximum will occur fairly close to the central fringe, and then the red light will occur further away and more spread out. So here, we'll do a video. You could work on this question yourself. However, one thing I want to point out is that there is an initial step that you have to do. You're going to have to figure out the distance between each line. So you're going to still use the same equation. You're still using the d sine theta equals m lambda, but they tell you here the grading is 10,000 lines per centimeter. So try to see how you can use that to figure out the distance between each line. All right, you can pause the video, work on this stuff, and we'll go over it in a second. All right, so like I said, the only real difference, you know, process wise between the diffraction grading and the double slit questions is that you're going to have to do one step before, and that is to take this grading and figure out this spacing between each line. Now, the way we're going to do this is by taking essentially the inverse of this. So here, all I did was convert the lines per centimeter to lines per meter by just multiplying it by 100. But the distance between each slit is just taking this and dividing it, doing an inverse, essentially, doing 1 divided by 1 times 10 to the 6. And we end up getting, in this case, that it ends up being 1 micrometer. All right. From here, I can then use the equation that we have, our interference equation, and we end up getting that the first angle occurs at 23.6 degrees, and the first maximum is going to occur for the red light at 44 degrees. And they want the second order, so I do the same thing. The second order for the blue light is going to occur at 53 degrees. And it turns out that the second order, even though it shows it on the screen, the second order does not occur. So these lines is not enough to get us a second order red line. That's something we're going to actually talk about later. Is we're going to end up doing something similar, but this time we're going to try to use the information to figure out what is the minimum number of lines we would need in the grading to be able to resolve a second line. All right. So now this whole thing is actually where spectroscopes come from. So as you know, we have this thing for called spectrometer or spectroscopes that we use in order to kind of identify different elements. So as you know, when light passes through a gaseous element or when an element is excited, it will either emit or absorb light. However, it turns out that each element emits and absorbs very specific wavelengths of light, and they come with certain patterns. They tend to act as fingerprints for that element. So what you can do is you could take a spectroscope or you could take a spectrometer and look at this sample. A good example of what I'm referring to is, you can look at a neon, not a neon gas, but or a gas tube where all the gas inside of it is being excited and now giving off light. And you could use the spectrometer to see, is the gas filled with neon? Is it filled with helium? Is it filled with hydrogen, oxygen? What is it? So you would look through the light that the gas is emitting with this spectroscope, and at the bottom or in it, you'll end up seeing very specific lines. And it's calibrated so that each line that's created will be placed at certain wavelengths. And you could use that to figure out which wavelengths of light are being created and then compare that to the known fingerprints of each element to figure out what element you're looking at. It also works for combination of elements. So here is an example of what a line spectrum would look like. This is what you would get when you look through a spectrometer or a spectroscope. So this is hydrogen. These are the color of lights that it'll emit when it's being excited. And then this is an example of mercury and sodium. And then this is just saying when the light ends up being absorbed by the gas, it ends up being the exact same lines being created. I think here it's a little hard to tell. It almost looks like this is supposed to be sodium hydrogen mix, but it's hard to tell with the lack of resolution. But basically, the lines are identical. So if this is your emission spectrum, where these are the lights being emitted by the element, then the absorption spectrum will look pretty much just like this. It would be a rainbow with black lines occurring here at these locations. All right, so use that in order to figure out this question. So again, we have the diffraction grating lines per centimeter, and then they tell us the angles, and we want to know what are the wavelengths that are creating each of these lines. So pause the video, work on this yourself, and we'll go over it in a second. All right, so all we have to do is plug and chug into the equation. We have all the numbers here. So, yeah, that's pretty much it. For the violet light, we get 410 nanometers. For this, we end up getting 434 nanometers, 486 nanometers, and then 656 nanometers. All these wavelengths do seem to make sense. Remember, violet to blue is around 400, while red is close to 700. So these wavelengths do seem to make sense with the wavelengths that we would expect. All right. So, so this is once again resolving power. So again, the idea of resolving two lines formed by a diffraction grating. Now, just like we said before, that the resolution needs to be such that we can actually take these two uh, lines and say, oh, these are two separate lines rather than one really big one. So this just kind of takes the whole phasor diagram and plays around with it to kind of come up with a resolution equation. What matters though is this last line here. So this is the resolving power. Basically the ability for a diffraction grating to resolve two lines of different wavelengths. What you're going to do is you would take the wavelength of the lowest wavelength, and then what you would do is you divide it by the difference between the wavelengths, and then that would get you your resolving power. Now, resolving power would also be equal to this, n times m, where n is the number of lines we have and m is the order that we're resolving. Like, is this the first order that we're going to resolve the lines for, or is it the second order? Obviously, the higher the order that we're doing, the slightly easier it will be to resolve things. If you have, yeah. So I'm just going to leave that at that. So here, they want us to resolve these two wavelengths. So use those equations. Pause the video, work on this stuff, and we'll go over in a second. So for part A, they want us to figure out the resolving power for this. So what I'm going to do is I'm going to take the difference between these, and I'm going to use this as my lower wavelength. It honestly doesn't really matter because you end up rounding the number anyway. But you end up getting roughly about 3,300 as the resolving power for the diffraction grating. Then for part B, to figure out how many lines we need to resolve it in the first order, we take this and we get 3,300 lines. Now, you'll notice that if I want to resolve this in the second order, then I would need more. I wouldn't need as many lines because, as you saw in the previous examples, that as you get to higher and higher orders, the spacing between the lines caused by different wavelengths gets bigger and bigger. So the higher the order that we're resolving, the less lines we need. All right. So here's another question. You can pause the video, work on this stuff, and we'll go over in a second. All right. So here they want us to figure out the maximum order that we can create that will end up being present for this wavelength. So this is goes back to what we did before, where we're going to use the equation, pretty much the d sine theta equals m lambda, and what we're going to do is set sine theta equal to 1 and find what the maximum value for m could be. Um, so what we do, we plug the numbers in. Again, we have to figure out what the actual distance between each slit is. But we use our equation saying that this has to be less, that the order has to be less than d over lambda. We get 2.26 when we plug our numbers in. So that tells me that the largest order that we are going to see is the second order. From here, what I can do is then find the width needed to actually resolve this. This will end up being the smallest width we need. So what we would do is we would need a resolving power of about 1,000 based off of these um, wavelengths. So since we can go all the way up to the second order, well, we're gonna use that to figure out how many lines we need. So we need at least 500 lines. Since we know that we're using a diffraction grating that's 7,500 lines per centimeter, we can use unit analysis to just take the 500 and divide it by 7,500 to get that the width of the grating needs to be at least 0.0667 centimeters. So again, you notice that we do kind of have to do a little bit more when we're talking about these diffraction patterns, mainly dealing with the diffraction grating lines per centimeter in order to find the distance between the slits, as well as introducing this concept of resolving power. All right, so X-ray diffraction is something that we can use to kind of identify the structure of crystals based off of pretty much how the X-rays end up diffracting. Like I said, if you go on through physics in Stony Brook, one of the things that they have you do is senior lab, and one of the senior labs is pretty much doing an X-ray diffraction through crystalline structures in order to figure out the distance between the atoms. It has to be X-rays because of the fact that the crystals are too small. So we end up coming up with a very similar equation to what we had before. This is called Bragg's equation. Um, yeah. So you can do this to figure out the structure and determine, the spacing between these two elements, essentially, or um, layers of lines. All right, so enough with diffraction. The last thing that we're going to talk about very, very quickly is this idea of polarization. So this is actually a property that's pretty much unique to light waves. It's something that definitely does not occur with sound waves. It pretty much only occurs for light, mainly because it's a transverse wave. In particular, it's a double transverse wave. If you remember, I said before that light's caused and created by the fact that it has a combination of a vertical sinusoidal electromagnetic wave and a horizontal sinusoidal magnetic field wave. So this combination means that it oscillates both in a vertical and a horizontal direction. So what we can do is we can actually create items and create devices that will actually block one of those two components. or even just a combination of some of both components as well. So this is just an example of what a polarizer would look like. So you send out unpolarized light, which would have light going vertically and horizontally. Like I said, the vertical electric field and the horizontal magnetic field. Then it goes through the polarizer, and what it ends up doing is it blocks out the horizontal component so that we only get a vertical out. Or we can send it through a horizontal polarizer so that we only get a horizontal thing through. Um, so this is just another example when we combine a vertical polarizer with a horizontal polarizer. We end up getting no light. It essentially cancels out all the light going through it. Um, we have an equation here that tells us about the intensity based off of the angle of the polarizer. Now there are actual natural polarizers. So when light strikes non-metallic surfaces at some angle, what ends up happening is that the light wave ends up being slightly horizontally polarized, meaning that some of that vertical light ends up decreasing. Now, what this actually ends up creating is glare in that excess horizontal component results in the glare as the light reflects. So this is what you would normally see as light bounces off of the surface because of the essentially the polarized light. If you ended up taking a picture of this surface of water with a polarizer that basically blocks some of that horizontal light, you'll actually end up getting rid of a lot of that excess glare, and you'll be able to see a lot more about what's going on underneath the surface. This is also the concept behind things like polarized glasses and anti-glare shields that essentially just gets rid of all this excess glare caused by the reflection of light bouncing off of the non-metallic surfaces. Um, so there's a thing called Brewster's angle, sometimes also called the polarizing angle. Basically, it ends up giving us total polarization at that special angle. Um, I'm gonna just skip this and skip this as well. Just talking about scattering light. So the main things to take away are the diffraction pattern equation, which pretty much is exactly like the interference equation. The only difference is you want to be aware that this diffraction for a single slit is talking about minimums, not maximums. So, keep that in mind. Um, and yeah, I didn't put it in here, but the whole resolution power, resolving limit of the circular lenses, of diffraction gratings, all that stuff, you want to make sure that you notate that stuff as well. All right. So these are the homework questions. They're due Wednesday. If you have any questions, please let me know. Otherwise, I'll see you later.